Hello, Flat Earth researchers, debaters and debunkers. Wait for a few people to join, even though it's probably Monday morning for a lot of you. But been doing some thinking and putting a presentation together about Flat Earth and how to do gravity mathematics. Hi, Celine Leon. All right, let me try and pop out the chat there. All right, lovely. Rudy, hi, good morning. Rose-tinted monocle, greetings. Okay, lovely to see people coming in. Hope you all had a good weekend. I'm not sure if it's still the weekend for some of you. Risky Poodles, hi. Yeah. Alexander Lightwater, hello there, hello there. Right, just looking for a, there we go, just looking for a lighter. I need nicotine to do this. Yeah, I wanted to really just do this present. This is a bit of a precursor really to a longer video that I'm going to, or in the process of making about the GNOME experiment. I'm not sure if you know about this. It was done back in 2012, 2013, but this GNOME was sent to different locations on the Earth, and it was alleged to kind of prove that gravity, the force of gravity, is different in various locations. Alexander, yeah, nicotine, yeah. Sorry about that. It's just one of those things. Apart from that, I lead a fairly healthy lifestyle. But yeah, being stuck on a spinning globe is never healthy, is it? It's very stressful. So being on a flat Earth is a lot less stressful. So yeah. What I've done here is I've taken some information from INFE. Hi. Yeah, buy gold and gems at the equator. Make a quick profit. In fact, I have a friend who spends a lot of time in Burma. He's made some very interesting discoveries with birds and what you might call dinosaurs trapped in amber that are taken from the mines very deep down. So in Burma, it's very they're very cheap, but obviously you have to know what you're getting into when it comes to messing around with gems. But I do plan to get that guy on at some point. He's a very interesting chap. So he's got some very interesting, information that goes against mainstream, what's the word when they're talking paleontology and geography, etc. So yeah, just to let you know, the chat is on a 10-second delay, but that shouldn't be too bad. So I may as well just get straight into it. Yeah, I'll kind of come back to the chat if you like later on. And I'll try and get through this in the way that I plan to do. The information I've got here is basically from NASA.gov and sciencing.com. It's all information that we all already know, but it's worth going through as a bit of a precursor, and we can discuss some of these things as we go. Let me try and I've got to try and see if I can see this. Rickus says, I found some pig bones encased in amber. They made a film about you. You had me there. Caesar, the solar eclipse shadow in South America moved from west to east again. Really? Ah, interesting. I didn't really follow that. It was very interesting to follow eclipses, etc. to start with. So sorry, I'm getting distracted by Skype messages. Okay, Nostri now. Hi Nick, battery low, but we hang out till the end. All right, hang in there, hang in there. All right, so I'll try and go through this fairly quickly. As I said, it's a bit of a precursor to a longer video, but I thought this was worth taking out in a section which basically debunks this whole idea of gravity. I've done a massive amount of research and data collecting to make these comparisons about this. It's Weather Police says it's late night on west coast of Canada. Oh, okay, all right. So still in time for the weekend, eh? That's cool. All right. Let me try and just make sure this is. Are you able to see this? Can you let me know if that's all being shown? This document is being shown all the way. It looks to me as if there might be a bit getting cut off. Not sure. Let me just have a look at. Oops! Oh, no wonder it's all messed up on here. Hang on. I know why. Just adjust that on the OBS. Right, that should make it better. That should be an improvement. Okay, that should be better now. You should be able to see the entire document. Okay, thank you, Rudy. Hi, Ute. Hi, Plane Ranger. Okay. All right, okay, lovely. Super duper. Okay. Yeah, sorry, still a bit of a novice with the old OBS here, but getting a bit better. takes some training, as with all this stuff, self-taught. So right then, let's just see if this goes through. Okay, hang on, I got to squeeze my own document window up so I can see what's going on. All right then. So okay, let's quickly go through this. I know this is going over stuff that we already know, but we'll just do it. So. This was on nasa.gov, and some of the other information is from sciencing.com. So it's really just to confirm what we are told as what gravity actually is, and why you would experience different weights in different locations. And this is in fact true. It is true that things will weigh differently in different locations. As I said, the video that I'm putting together will demonstrate irrefutably that it has nothing to do with being on a spinning globe and the idea that we've got gravity. So we'll do this kind of precursor. It's just take. Hi Tom, Budas. So the question on this NASA website: do you weigh differently at the North Pole than you do at the equator? And of course the answer is yes, you do, because at the equator the centrifugal force due to the spinning of the Earth is at its maximum and vanishes at the poles. This means that the attractive force of gravity is slightly reduced because it is directed towards the center of the Earth, while the centripetal force is directed outward from the center. So, usual stuff, but it's also good if there are any kind of newbies looking into this to consider. Of course, we have to have this idea of an external force of gravity to have us do what would otherwise be physically impossible, right? Stick to this spinning ball, we'd either fall off or we'd fly off. And of course, it is all connected with the idea of having the Earth somewhere in space. So it really is just this abstract concept. So of course, the way they describe it, this red text is from sciencing.com. So the circumference of the Earth at the equator is roughly 40,000 kilometers. I always find it funny that they use the word circumference, because of course we know that can refer to the edge of a circle. So, and we know that Eratosthenes is supposed to be the guy that decided on the circumference because of the sun. So, of course, for anyone that's new to this, if you go and look at how the globe Earth was put together, how it was created, it's all about looking up at the sky and determining the dimensions. Hi, Boris Chops. Determining the shape, dimensions, and alleged movement of the Earth from there. Steelman. Steelman, okay, saying what word would you use to refer to the distance around the equator of a globe, Earth, if not circumference? I'm not saying it's wrong. All I'm saying is the word is interchangeable. Of course, yes, you use the word circumference to talk about being around a sphere, but you also use the word circumference to talk about the edge of a circle. So if you're using the sun, the circuit of the sun, to define the equator, well, that's as far as you need to go, isn't it? So yes, they can say it's 40,000 kilometers, the circumference of the equator, but that doesn't dictate that it's a globe or a flat Earth. It's just that area above which the sun goes. In my mind, the sun is going above the flat Earth, and in every other flat Earther's mind, we've pretty much realised that that's what's going on. So you don't even have to debate it. When people start debating the sun and the distance and the size to the sun, it is ridiculous to do that, because it is arbitrary. You just cannot know. Nobody knows. But of course, this is part of the math magic, is that you can talk about angular size and say actually the sun is 400 times larger and 400 times further away than the moon, but its angular size is this much, and we know that twice the distance means twice less angular size, etc. So you can, that's where the math magic, part of this math magic is. You're taking real life mathematics and applying it to these intangible objects in the sky, and this is part of this imaginary model based on creating a model from looking up at the sky. INFE says original ball Earth is a contrived size. It is just 360 degrees times. Yes, okay, I was just getting to that. 60 minutes per degree to 21,600 units, nautical miles, then 21,600 times 1.15078 miles equals 24,800. Whatever that number is, 24856.85 circumference there. Yeah, exactly. This is all is basically what we're going to look at here as far as manipulating those numbers. Yeah, that's some big tape measure they got, says Risky Poodles. Ricus Vaticus, don't forget it's not a circle, it's oblate. Yeah, okay, of course, that is part of the issue here when it comes to realizing that this alleged centrifugal force is going to create some oblateness. And yeah, so I'll just, that was just basically the first point there. Of course, the circumference of the Earth is, you can use the word interchangeably, and of course the equator would just be the limits. So you have your circle, and then you can go outward from there. So I would say that if when we see this globe rotating, we see this massive stretch of ocean here, which has these what do they call them? Poles, or pole of inaccessibility. Basically, there are places on this ocean that we see on the globe that people just don't go, so no one can ever confirm what is there. So once you go beyond the equator, there is very little land as well. However, Antarctica is actually mapped out, or where it actually is in relation to those other land masses. You could basically cut all that out, and you could create this. So you could, it's like what's the word? Not origami. Similar to origami, but when you take flat pack shapes and fold them, so you've got your roundness as far as the equator goes, from the North Pole to the equator. But then again, we don't really have anyone going to the North Pole, so this is all arbitrary anyway. But creating this globe map is once you have that circumference mapped out, you can cut and fold and whatever to create your globe. So yeah. Anyway, of course, as who is it who mentioned that just now? Hi, Richard Archer. Yeah, INFE. As you said, this whole idea of 24 hours. I mean, this is obviously stuck in our heads. from a very early age that a day is 24 hours. But of course, we know that we never really get day and night that are equally 12 hours. So once you can separate, part of the process of realizing we're not on the spinning globe, of course, is to separate the idea that night and day are created by the motion of the Earth, rather they are created by the motion of the sun. And of course, the moon can do its own thing, and it's not always coming out at night; it's coming out in the daytime too. So yeah, let me just go down in the chat there. Oh, hi Celtic, good to see you, man. Nostri now, Harry Groler did a great vid showing the math magic involved in the circumference sums. Worth a look. Nice one. Okay, thank you. Yeah, Harry Groler. It's really nice to see what Harry's doing there. Great stuff. Lone Zen Warrior. Hi. Look up how many miles there are and how different each is. Statute, empirical, nautical, etc. Then meters based on the speed of light is all convoluted. Absolutely. Yeah, definitely agree, Celtic. Harry Growler does great work, and this is wonderful, isn't it? You know, someone did a hit piece on me yesterday or the day before, and it's just insane because you've got all these people just hurling abuse and being nasty and the usual rhetoric. No one's got any actual science, and of course they debunk things that you can actually create in reality. You can actually create shadows on a flat surface, and then they go and draw pictures and say, no, these pictures are reality because I can do the math. Whereas you can actually demonstrate with a local light and shadows that they work on a flat surface. Yet they'll go back to their cartoons and say, no, that's not reality. What you're demonstrating with a practical demonstration isn't reality. This is reality on my computer screen. It's nuts. Something's happening here. I'm spinning again. Okay. Yeah, all they have is ad homs, Celtic. Yeah. That's right. I mean, I would be apt, and this is part of the thing, isn't it? When you see that they don't have any science, all they've got is the ad hominem attacks, then you realise that we're dealing with a belief. Any road. So yeah, of course, you have to factor in this idea that speed equals distance divided by time. So thus at the equator you would cover a greater distance in 24 hours than at the poles. And it's an amazing difference in the speed. At the poles you're covering no space at all. I mean, even this, the amount of distance you travel compared to being on an imaginary pole to on the equator is just immense. It's just absolutely nuts. 0.00008 kilometers an hour on the poles and a rate of speed at the equator of 1,667 kilometers an hour. Absolutely nuts. So if there are any globers watching, this is a great one. We've all heard this one. Imagine you're on a train. This must be one of these things that they tell you about in school. I think maybe it's because Einstein was apparently sat on a tram when he had his revelation about the speed of light. Richard Burke, hi. Alexander's, this is worth reading, I think. Alexander's saying, yeah, you imagine, exactly. Ever since my FE insights, I have regularly seen that when moon and sun at the same time in the sky, the phase of the moon is off regularly, but last January it was way off. Oh, interesting. Okay. Risky. Yeah, so imagine you're on a train. So, of course, I'm sure most of you in the chat or watching have already thought about this. You know what I'm going to say. But, of course, being on a train, yes, it's real physics if you're moving and it's all high sparkily. If we're moving and there is no disruption, then, of course, it is no different. This is, of course, one of those logical fallacies. It's a straw man, to say, well, we're moving, but you don't feel it. And, of course, that's linear conservation of momentum. No one denies that this is real physics. That's just a fact. But, of course, with the globe, we're talking about angular momentum. And that, of course, this is why we talk that, and this is exactly why they use the word well, okay, we're talking about the rate of speed, and just, of course, you have to use the word acceleration, because acceleration is it's not a constant speed, is it? You're constantly being taken in a new direction. So being on a globe would mean constantly changing direction. So that would mean constant acceleration. So it is not the same as linear conservation of momentum. Yeah? um, Hang on, is someone saying it's cut off? Let's have a look. What's happening? Oh, what's happened there? Why does it keep doing that? I have no idea what's happened there. That's weird. Sorry. Okay, thanks for shouting that out. I have no idea what went wrong there. Yeah, Boris Chops. Yeah, good point. That they say the what is it? Equatorial mounts single-handedly prove the globe. No, not at all. You've got these two axes, and of course, if you watch something go overhead, even if it's going in a straight line, you're going to follow this arc. I can't understand why they even use that as an argument. It is mental. Yeah, therapy channel inside the train represents an enclosed system. Try to jump up on the top of the train to feel the difference. Yeah. So, okay. So the effective acceleration of gravity at the poles is, again, acceleration. It's one of those important words that we got because, okay, we're going to come to that. We're going to come to that in a minute. Is 980.665 centimeters per second squared, while at the equator it is 3.39 centimeters per second squared less due to the centrifugal force. So they tell us that, they are mental. They tell us that if you weighed 100 pounds at the North Pole on a spring scale, at the equator you would weigh 99.65 pounds or 5.5 ounces less. So it's actually only a 0.35% difference in the force of gravity. As I said, the video I'm putting together is going to demonstrate how this calculation, it's not a measurement, this calculation is totally off. So that's going to be good to debunk that. But this is a really important thing that they say here. And this is where the kind of the math magic starts. Your mass in grams, however, would stay the same because grams is a measure of the resistance of a body to being moved, inertia. And they say it has nothing to do with acceleration or gravity. Your mass in kilograms would weigh the same. So it is common for people to use pounds and grams interchangeably, but they are not. Sorry, Blissful Zombie, I'm going to show your comment there. So it is very clever actually what they've done here, because although we always use the metric system, grams and kilograms, to refer to mass, the mass is not determined by putting something on a set of scales and weighing it. It's determined by the volume and the density. Tom K. Fly, we don't feel the angular acceleration because it's only for... No. Do not use that straw man argument. You cannot say that it's moving, but you can't feel it. Yeah? That's just... You can't say it is, but you don't feel it. There is no measurement of it. So we're going to go through why this is all assumed and created. So I felt it was really important to put this observer water high. Okay, cool. Just make sure that it's still okay. It still seems to go right. Definitions. Okay, so again, really, this is just, I went through this and I thought it's a great thing for newcomers. I know a lot of us have already been through this and we've thought about it and we've had this realization about how the the descriptions are used and how obfuscation and confusion is used. So, all right. So what we got is, let's just take now. What I aim to do with this presentation here is just to demonstrate that, of course, all of this works in the real world as far as measuring tangible objects, and it's very accurate, and it works for calculating things. It works for engineering or aviation or whatever you want to. It really does work in the real world. However, we'll also see from this that these definitions, how they can be used to create this abstract, imaginary, mathematical model and have us believe, have this connection and have us believe that it relates to reality, because of course we are using these real life definitions and terminology. Okay, so it's accepted that this works in the real world, but it's also a realization that all these things can be used to create imaginary scenarios. So this imaginary scenario here that we have is, hi John Patterson, we have this cube. Now it could be any dimension that you like. It could be a centimeter by a centimeter, it could be a meter by a meter, whatever the dimensions, okay, but it's uniform, and it could be made up of any material that we like. We can just imagine that. So first of all, we talk about the mass, which, as we said just now, was inertia. And as it was pointed out in the NASA text, mass is not weight. Okay, it's not used to talk about weight. So we don't weigh something to determine its mass. But it is still measured in grams and kilograms. So of course, if we're, I'll just go through this, the fixed or constant amount of matter in an object, that's basically the definition of mass. There we are, this orange block of whatever material it is. And its resistance to acceleration or tendency to remain at rest or remain in motion. So that's the inertia. And of course the size can vary. So for example, we can say that the mass of the orange cube is 1 kilogram, but we haven't determined that figure by weighing it on scales. What we use are these definitions below to determine the mass. So we use volume and density. So volume, of course, is the dimensions, the space that it will take up. And of course we talk about three-dimensional space because we're talking about three sides, the height, the width and the breadth. Okay, so these are equal length, and this is why we use centimeters cubed or meters cubed, cm3. So just by putting this suffix on after the number tells us that we're talking about volume, just as if we put the suffix kg or g after a number here, then we know we're talking about mass, but we didn't weigh it to arrive at the mass. So again, we can assume that this cube is 1 meter by 1 meter by 1 meter, and then we can arrive at this assumed volume of 1 meter cubed, 1m3. The 3 simply because we took 3 sides. Yeah, so that's fairly straightforward. We've all learned it in primary or secondary school, whatever, but it's worth just going through. And so then we come to density, which is the real definition of weight. So they define density as the amount of mass, again using grams and kilograms, in an object per unit volume. So yeah, the density is basically the mass and the volume that we've talked about here put into this one formula or equation. So I'll try and keep this visible. Yeah, so basically we want to know the density. We just take the mass and we divide it by the volume, so that we can assume that the density of the orange cube is 1 kilogram of mass divided by 1 cubic meter. And of course we use the suffix here to talk about density, kg, to know that the kg is referring to the mass, and this is telling us that we divided by the units of volume, meters cubed. Now, excuse me, just a moment. So, of course, for the mathematician, this is excellent. We've got this metric system which is easily divisible into ones, tens, hundreds, thousands, and this is why kilograms are used instead of pounds and ounces or meters. And we're going to get on to talking about water in a minute. Because it's all interchangeable, so this allows us to, and we'll get to the newtons in a minute as well, Tom K. So, yeah, of course, we can calculate the mass of the orange block from known or assumed density and or volume. So, for example, if we didn't know the mass but we wanted to work out, we've already gone and weighed it to get the density. So this is, basically we put it on the scales and we're getting the weight, and that is basically referring to its density, which of course is interchangeable with mass. Let me just check that this is okay. Right then. So yeah, we can calculate the mass kilograms of the orange block from known or assumed density and or volume. So basically we want to find out the mass. We basically take the density and multiply by the volume. Just now, to get the density, we divided the mass by the volume, so we want to find out the mass. We multiply the density by the volume, and of course we get 1 kilogram times 1 meter cubed, and we get 1 kilogram. So of course here we've got this kg. So what really are we talking about? We're talking about the mass or the density. They are both, of course, interchangeable, and on the Earth they don't change. Every measurement that is made is basically going to be the same in this respect. Mass and density are going to be pretty much the same. FWL said the tracking monitors in my telescope prove a stationary Earth. Yeah, cool. Now, just to kind of go back to school a little bit, if that cube was an aluminium cube, we would of course say that the density of an aluminium cube would be, say, 2.7 grams per cubic centimetre. All right, sorry, just a minute, got to... Now, half I take aim now. Sorry guys, just a second. Just had to deal with something there. All right. So where were we? Okay, so if we go back up and have a look at that cube again. So let's just imagine now that this cube is 1 centimeter cubed in volume, and it's made of aluminium. Then of course the density of the aluminium cube is going to be 2.7 grams cubic centimeters. Of course, here, by using this suffix again, we know that we're talking about the density, the mass in grams, and its volume. So we just know that we're talking about the density. So to arrive at the description of density, we took the mass in grams and the volume in centimeters. And so, of course, we can then talk about the mass of the aluminium cube also being 2.7 grams. But here, by just using the G instead of we're talking about the cubic dimensions, then we're talking about the mass. But of course, we can also talk about the weight, in which case we are basically talking about the density. Yeah. And that is also 2.7 grams. So although they have this rule that when you're talking about mass, you're not talking about its weight, they still use the G to talk about the mass. And when we talk about the weight or the density, we're using the G, and it's going to be the same. Yeah. All right. So again, it would go on with the density of an iron cube would be 7.874 grams per cubic centimeter. It's heavier. So you get a cubic. This thing. This cube doesn't change in dimensions, but of course the mass and the density will change depending on the material it's made of. But you wouldn't, if you weighed it, you'd say, oh, I'm getting its weight in density. And you wanted to talk about its mass, you would have to say, oh, well, I arrived at its mass by taking its volume, its dimensions, and knowing that aluminium or iron has a certain density, then you can just apply that. So we can simply imagine or perceive that this orange cube is made of whatever. It's made of steel or aluminium or iron. As long as we know the density of those materials, we can then go ahead and say, oh, it's got a mass of 2.7 grams, or it's got a mass or a density of a mass of 7.874 grams, and you stick it on a scale and it will weigh 7.8 grams. Yeah. So you see what I mean? We can just imagine it. We can just say this is made up of any material that we know the density of, and give it a weight and give it a mass and give it dimensions. And of course we can see how that can be done when we're talking about the moon and planets and the Earth itself. Because obviously this is why we talked about the Earth in the beginning, because once they have this 40,000 kilometers of the equator, they can then, obviously we're talking about a spherical mass, and I'm not a mathematician. I'm just but I can see how it all fits together. But of course, I'm not going to start doing spherical mathematics on a live stream. But I can handle mass, volume, and density on a live stream with a cube. Okay, so yeah, but you get the point. If you can do the spherical mathematics, you can then basically make it all up, because we essentially have the volume. We essentially, when it comes to the Earth, we've essentially got this idea of the Earth's volume or size, because we know the equator, whether it's flat, round, or whatever shape it is. We've got this boundary that has been determined by the path of the sun. So you say, okay, the Earth is that big, and we'll do all this mathematics, and we can assume the Earth's volume. We can assume its size. We can assume the amount of space that it takes up. And so we've got this part of the equation, the dimensions. And then, we can obviously think about what the Earth might be comprised of and talk about its density. And you can then make up these figures and say what the Earth's mass is without having to weigh it. So this is what they've done with it. This is what they've made these mathematical models that are based on these tangible things and real maths that works. I can never remember. Do the English say math or maths? I think the English say maths and the Americans say math, right? I'm not sure. I can't remember now. Yeah. So here we go with the force of gravity. So I'll try my best to try and, obviously go through this. Again, I know I'm preaching to the converted. I'm not trying to teach anyone anything. It's just putting it into a logical order, so that anyone new to this can see how the math magic is done. How it works in the real world, but also would appear to work for the models. Yeah. Okay. So Yeah, some people arguing some amongst themselves. I'll come back to the chat later on. I need to kind of get through this. So of course we understand that the force of gravity is called newtons. Now, just to go back, of course we had kilograms and kilograms in the metric system, and we had meters and cubic meters, okay, as our suffixes. But now, of course, we've got this new suffix introduced, which is, the external force to give the mass weight. Yeah, they're always telling us that mass isn't something that you weigh. It is basically the density of something. So in order to have it go in any particular direction, then of course you need a force. So yeah, let's just go through the definition that it's given. This is kind of a doctored official definition of what gravity is. So it's the external force. I put the parentheses in myself. Needed to push. Again, this was not included. They don't use the word push. They'll often just use a different word or nothing at all. Hi Paige, and hi Wobbly Boost. I'll come back to everyone in a sec. Orbs Realm, hi, nice one. And 101 Rock Hound, good morning, good morning. So the force of gravity is the external force needed to push 1 kilogram of mass and accelerate it at a rate of 1 meter per second squared, distance over time, in the direction of the applied force, which of course is usually down. So again, this is why we have the introduction of the metric system. This is all part of the new ton. Whether this was a person that actually existed, what we have is this introduction of the metric system, basically a standardization of everything. And some of the kind of first research I did when I started getting into this that I didn't know at first was that Newton was apparently the head of the Royal Mint for a long time. He was also responsible for introducing the gold standard for the British monarchy. So his job basically was to standardize everything. So of course, using spheres and circles is an excellent way to standardize everything. I think it was INFE that said earlier on, when you have this globe and you have 24 hours, of course 24 is easily divisible into circles, 360 degrees. So this allows you to really play with the numbers. If you decide that the Earth is a globe, then you've got your 360 degrees. You can divide it up nicely into 24 hours and the time zones and all that stuff. So it is all very easy for the math magician to then go and manipulate. But the simple fact that we for example, I don't know what it's going to be like in the UK right now, but when it gets to midday in the UK, is the sun at its zenith? Likely not. It will likely be at its zenith at maybe, say, 1 o'clock in the afternoon, which in itself tells us that these time zones are not in sync with the idea that we're on a globe going around the sun in this heliocentric solar system and the Gregorian calendar that was created alongside it. So, when people say, oh, we've got a working model of the globe, no, you haven't, because it doesn't fit with the time. If it's 1 o'clock or 2 o'clock in the afternoon until the sun is at its zenith, it means the clock is out. You are not on a real time. You're not on Earth time. You're not on, you are on Earth time, but you're trying to follow the sun's time, but it doesn't fit with reality. It doesn't fit with observations. Yeah? So that's just another one of those things. I mean, I've even heard people say that time zones prove the globe, and it's like, oh my God, they haven't even got as far as looking into that and how this has all been divided up. Right, let's just get back down to here. So again, the newtons is one of these suffixes that's used instead of kg or meters or whatever, but of course it relies on having the metric system in place. Again, just to drive the point home, the force of gravity, or newtons, is the external force needed to push 1 kilogram of mass. Again, we're told that mass doesn't weigh anything until it has a force acting on it. Yeah, but of course a mass is this. It's based on a mass that is 1 kilogram. It's just double speak. This is 1984. There's this introduction of this idea, which of course, this is why people feel that they're smart to understand how it all works, because you've got this introduction of this unnecessary element that allows us to imagine being on a globe, or imagine that something with mass doesn't have any weight just because of the way it's been defined until there's a force acting on it. Because you don't determine the mass of something by putting it on a pair of scales. You put it on the scales, you get 1 kilogram, but it will be determined by the density or the volume. They say, oh no, that's not its mass, that's its density, that's its weight. Yeah, so this is the thing. We are given this. We have to make this extra leap in order to use this idea of gravity. And of course, Newton was so celebrated for bringing this all in, because he finally found a way, after however many hundreds of years it was, to have us perceive and believe what we know is physically impossible. It's like, hang on a minute, we've got this heliocentric model. And because we've got a heliocentric model, we have to have a spinning globe to justify night and day. But how the heck are we going to get people to believe that you can stick to a globe? How does that work? So along comes Newton with a whole new descriptor, suffix to add, and a way to perceive mass and weight and density, and then say, oh, it's this external force based on 1 kilogram of mass, and accelerate it at the rate of 1 meter per second squared in the direction of the applied force, down usually. So Newton's is used to define gravity on Earth, because the orange block that we saw, the orange block is here, falls through the air, accelerating downward at 9.8 meters per second. So of course, what we now have is this rate of acceleration, the time and distance applied to force. But of course, if I don't know, let's just hold something up in the air. I've got an ashtray here. If I just hold this up, what kind of force are we talking about here? Because okay, there's a force being used to hold it up, but this isn't accelerating anymore. Yeah, it's not going anywhere, so there is no time involved. There's no acceleration involved. So what do you say about that now? Why would you then say its weight is caused by an external force making it accelerate when it's not accelerating? It's at rest. Or if it's on the table, it's at rest. Yeah? So, yeah, we have this whole thing. We have this idea that weight is created by this external force of gravity, but this external force of gravity is based on the time it takes for something to fall through the air and the rate of acceleration that it falls through the air. Well, that all falls apart as soon as it stops and hits the ground. It's different then, or it hits the water. Yeah? So this in itself is just, it's just out there. So an example in orange here, example of force acting on the orange block, which again is called gravity on Earth, which is 1 kilogram. So we've ascertained that this block is 1 kilogram. It has a mass of 1 kilogram. And then, of course, they apply this 9.81 newtons, which is merely just this, the rate of acceleration that something will fall, so they use that and call it a force and call it newtons, and actually they can round it off to 10 newtons. Even physicists will do that in their lectures or in their calculations. They'll round it off to 10. So really all you've got is a simple conversion of 1 kilogram being 10 newtons. Whatever its weight is, whatever its mass or weight or density is, 1 kilogram, you just add a 0 and you've got newtons. That's it. It's just a fancy way of arriving at, and of course, you then divide it up. It's just fortunate for them that things fall at a rate of acceleration that's very close to 10 meters per second per second. Makes it all a lot easier to work with. Yeah. So it's really quite funny. But do you see what I mean? Do you see why Newton is so celebrated for being able to conceive this imaginary thing and then claim that mass doesn't have weight on its own unless it's got an external force? So, of course, when it comes to the force of gravity formula, they basically need this always excuse me, always happens. I gotta stop shouting. Well, yeah, we need to do the formula. They need to have mass 1 and mass 2, and the distance between the two masses. Oh, sorry, I've missed out this whole thing here. Newton's law. All right, maybe it's excuse me. Right. This purple text. Newton's law of universal gravitation. Every body of mass attracts every other object in the universe. Absolutely ridiculous. If anyone's going to mention the Cavendish experiment, all you've got to understand is that like attracts like. So if you're going to use a couple of iron balls, there are some magnetic properties in those that will bring them together eventually. Yeah, it's just you put weight on something, things are going to happen. Yeah, but this law, this is a law. It's just like, and this is why awake people can get this, is because they've gone through this process of understanding that we have this whole system of laws that have been created by men or people or man that kind of try to replace natural laws and insist that because you're born in a particular society or you have a driving license or whatever it is, you've got a birth certificate, then you are bound to the laws of that society. So what we have with Newton's law of universal gravitation is nothing that's a natural law. This is not an explanation of what really happens. This is just a law that was made up for the globe, for the global system, for the globe standard, just as Newton created the gold standard for coinage, the British coinage, and many other things. They've standardized our lives. They've standardized everything. Everything is standardized, isn't it? The metric system. It's okay. It's great. It's great for doing all the calculations. It facilitates all these things. Making measurements, and as I said right at the beginning, it works in the real world. It's wonderful for engineering, for aviation, for whatever you might want to use it for. It works. But then we have this law applied for the imaginary scenario of trying to dictate where we are, what this place is, and its place in space. And yes, we can all imagine being on something that is in space. And so, of course, if it's going to go somewhere, you have to push it. Yeah, we get that. But, this is why the whole idea of space has been promoted. simply to try to describe this creation story and have us follow this belief about our place in the universe. Where are we? Oh, we're on a globe. Yeah? So this law it's just created for the model, not for reality. It's not a measurement of reality. And of course, people will believe that it's a measurement of reality because, of course, I'll let my kid just stop doing that, because I did tell my wife I was doing a live stream, but maybe she's being sarcastic by allowing the kid to do that. Time. Again, because we've got this whole thing here. Again, the external force to push one kilogram of mass and accelerate it at a rate of 1 meter per second squared. Distance over time. Okay, we've got this incorporation of time into this law. So of course, when they can measure the time that the sun takes to rise and set, or the moon, or the star, the planets, what have you, the luminaries, when you have established the time, just as we saw with all these other things here, the volume and the mass and the density, when we have these properties worked out, or we have one or the other, then we can then create these formulas which appear to work and give us these real world answers. So of course, when you introduce the idea of time and acceleration, then of course you can apply that to this law, and then say, oh well, it's so we've got the time it takes, and then we can apply this. We can apply dimensions. We can apply volume. We can apply mass and density. Yeah. So again, when it comes to the formula, they say mass 1, mass 2, and the distance between the masses. If you want, for this law, for Newton's law of universal gravitation, that every body of mass attracts every other body or object in the universe, what you need then is one mass, which mass 1 is the orange cube, and then mass 2, which of course is going to be the Earth, and the distance between those two masses, or the center of gravity of those two masses. And of course, we've already got the dimensions of the Earth, the alleged volume, because they already worked out that the equator circumference is 40,000 kilometers. So then they can then create this volume and attribute it to their spherical Earth. So they got that, yeah. And so when the mathematician does his equations for working out mass, or newtons, or whatever, then of course we already know that something has a weight or a mass or a density of 1 kilogram, and we're going to call it 10 newtons. And the thing is, with mass 2, what you'll see, this. So they tell us that the Earth is 5.9 sextillion tons. So they've got their mass, they've got their density. Again, they didn't have to weigh the Earth, and no one's going to demand that they weigh the Earth to give us this figure, because they've got the dimensions, they've got the volume. And of course, they're going to say, oh, well, we've got this iron core, and we've got this mantle, and we've got this crust. So we have all these elements, such as aluminium, steel, and all that. Again, if I just go back up to the top here, remember we talked about how we know the density of certain things. We know the density of aluminium, we know the density of iron per cubic meter or centimeter. We know all this, and we can talk about it in terms of mass or density or weight. Yeah. So all they have to do then is, once they've got the volume of the Earth extrapolated from the circumference, yeah, and then they can say, oh well, the Earth has got this, this, and this, and this in it, and we add all that together, and ta-da! We've got the mass of the Earth, and we can say, oh, it's 5.96 trillion tons, and no one's going to bat an eyelid. They say, oh, scientists know, they know. They didn't have to weigh it either. No one's going to demand that they put the Earth on a set of scales. And this is why they laugh at the flat earther who says, have you weighed it? Have you weighed the Earth? How can you verify it? Oh, we just know, because they know that they have the descriptions, they know they have the definitions in order to justify the model. To them, it's rock solid. You can't refute it, because they know the times that things take. And they say, oh, it's XX mass. We know that because it's XX size, XX distance. We've got all the formula. We can work it out to the millimeter. And we believe them because we can't refute it, because they've got it all nailed down. Yeah? And it all works. It works in the real world. That's the thing. And so the mathematical model is created, and it seems to work. Yeah. So that's that. Now, I did want to talk. Let me just check that this is still streaming okay. What is really interesting about this, though, is that, of course, the whole metric system is based on water. And of course, the whole thing about water, bendy water, is very funny to a lot of us. Yeah. But it's because obviously water was this abundant source, an element that they could use and contain relatively easily. But this is the whole foundation. It's, you know, the measurable properties of water are the foundation of the metric system. So although it's a fluid, and the entire metric system is mostly used to talk about mass, density, volume, yeah, it's based on water. So we have mass defined as 1 litre of water is 1 kilogram. And the volume, the amount of space that 1 litre of water will take up, or 1 kilogram of water, it's the same. Yeah, so what you get is 1 cubic meter of water is 1,000 litres of water. So this, again, we've got the metric system based on this, and you can divide it up into your units of tens and ones and thousands and hundreds of thousands or what have you. Yeah, it's wonderful. Yeah, and of course the density, ergo weight, of water is the same as the mass. 1 litre of water weighs 1 kilogram. So the whole thing, the whole metric system, is based on having yourself a cube of water. And then it goes on. Yeah. So it's just an interesting side point, but the density of water depends on temperature. So the maximum density of water is 4 degrees centigrade. And just another little factoid for fun, the density of ice is not like other solids. Although it is a solid, because it's made from water, it's different. It's about 9% less dense than water, so it takes up more space, more volume, and then so it floats on water. Yeah, so basically 1 litre of ice weighs less than 1 litre of water. It's just an interesting thing, because although it's a solid mass, because it's made of water, it doesn't behave like all the other masses. Is Chadwick in the chat? Oh, Pendle, hi. Cheswick, nice one. Okay. Now, what I thought was really cool, I've done this before, but it's worth repeating, the density of oil. So, of course, we all know that oil floats on water, and because the density of oil is less than water. So, for example, one cubic meter of oil has a density of 800 kilograms per cubic meter, whereas 1 cubic meter of water has a density or mass of 1,000 kilograms per cubic meter. And we can interchange density and mass here when we're talking about water, because of this fundamental foundation of the metric system, that the mass and the volume and the density of water are all the same. Yeah, a kilogram, a litre, what have you. So basically, yeah, you get a litre of oil. It's going to weigh. It's very close, because we're talking about cubic meters. If it's 800 kilograms per cubic meter, so even if you have a litre of oil, it's going to be very, very close to the weight of or the mass of a litre of water, but it's slightly less. The density is less. So of course it floats. Now, what is really cool about this is that an even greater volume or mass of oil floats on water. This in itself totally debunks gravity. It totally debunks it. Why? Because it doesn't matter how much oil. You could put you can have a huge volume of oil or mass of oil floating on top of a tiny thing of water here. Yeah? So here we've got you can see here, it's just one small layer of water. And you can put as much oil as you like on top of it. So there is no force pushing or pulling that oil down, no matter how massive the oil gets. It is not going to go below the water. It's always going to be on top. This debunks gravity. This. Yeah? Because they tell us that gravity creates weight. They say that gravity gives weight to mass. Well, we've got more mass in this oil than we have in the water. The water's a tiny mass, the oil is a massive mass. So where's the gravity? Where's the gravitational force acting on the oil? There isn't any. Does not exist. It only exists in order to have us believe this tripe here, that we know is physically impossible, sticking to the outside of a spinning ball. It's the only reason you have to have an external force. It's the only reason that they talk about mass. And they say you're not allowed to say that mass is weight. Yeah? This is a cardinal rule of theirs. Mass is not weight. So of course they can tell us that with our whole Newton's laws that they made up for the model, that with a moon that is smaller, less dense, again they can just extrapolate it's this size, angular size, geometry, it has this mass, this volume, so we can say it has this much density. Yeah? And sorry, I'm getting in. Yeah? Is it? Okay, yeah, all right, 5 minutes, yeah, okay. All right, I'm going to have to pick up my kids soon, but we will not, I was in mid-flow there. But I think everyone's getting the point, yeah? I'm really hoping that if you're a newbie to this, you're seeing how this math magic is done. And how, to your average globe defender, it is their reality, because it is a tangible reality. Because they have their descriptions. And it's infallible in the real world on this earth. But then, of course, they can say that the moon has this, they can kind of pretty much determine the size of the moon. And they can say, right, we've got the dimensions, we've got the volume, as we have here. We've got the volume of the moon. And we'll talk about the density and give it weight. Then we'll add Newton's law of every body, every mass. We know, maybe they can work out the distance. Maybe they know it. Maybe it's a scientific fact. Maybe it's measurable. So they've got it. They've got the distance between the Earth and the moon. They've got the size of the moon. And then they've got the time it takes. And they can do all the math and it all works out. And you can't, they can't prove it as being physically true. Well, they feel that they can because it's observable. We can't disprove it either. That's the infuriating thing. But of course, for the Globie, they can't see it any differently. They can't perceive it as being any different because it's been drilled in since we were kids, and it's the law. And we're all good law-abiding citizens, aren't we? So we abide by the law. Yeah? Newton's law, by royal decree, no less. Yeah? Newton's law, created for the model. Newton's, created for the model to give mass weight in other places apart from the Earth. Yeah? All right. So, I think, again, and one more thing about the whole density thing, and how when they go in the zero-G plane and then they fall through the air, and the oil, the density tower goes everywhere, it doesn't settle. It's like, well, you think about that. You're falling through the air at obviously a greater rate than of acceleration. They can only do it for so long. They have to do this parabolic curve, yeah. So they can only do it to a certain limit, and everything goes haywire. There's no layers of density, and they say, you see, proves gravity. It proves that everything is being pulled down. But then you hang on. You're saying that the Earth is spinning. How fast was it? The Earth is spinning at 1,667 kilometers an hour. The Earth is flying around the Sun at a greater rate of acceleration than that. So you're saying that a density tower not settling when you're flying through the air at not that great a speed proves gravity, whereas the Earth is supposed to be going a lot faster or at a greater rate of acceleration than it takes to upset the density tower, yet everything on the Earth is layers of density. Again, goes back to this nature, natural science, natural physics. This debunks the globe. This proves that we are on a stationary, level Earth. We are not flying through space. If we were flying through space, nothing would settle, because even the force of gravity wouldn't grab it fast enough. Okay? So listen, I got to leave it there. This has been fun, and as I said, this originally was part of a longer presentation that I'm doing with information about this gnome experiment, and it's about the first time I know of where there's been an attempt to actually weigh something in different locations and record the weight of the equator and the poles. And there is a difference, there is a difference, but we will see from the data I've gathered that it doesn't fit with the globe. So let me just try and, I'll just go through everyone. Really appreciate you joining me. Boris Chops, Desert Diagnostics, Flatfish, Guess Who, INFE, Lone Zen Warrior, Listexic, Mr. Cheswick. Miss Cheswick, I'd love to do the trumpet with you one day, or the harp. That would be fun. Send me some chords, and we'll do something. Nathan Oakley, hi. Nostori now. On a Plane, Orbs Realm, Paul Hoxton, Paige, Pendle, Eldnep. Lovely to see you, Pendle. I was thinking about you the other day. Really good to see you. Love your poetry. Leave us a nice comment, will you? Just get some poetry out. Risky Poodles, Rudy Marley, Rune, Selen Leon, The Sun Revolves Around Me, Trouble About and Ute. All right, so thanks ever so much for coming along, yeah? And hopefully, I hope you haven't bored you to death by taking you back to school. But to be honest, I find it fascinating just to get it all really nailed down and clarified. And hopefully it will help those who are coming into this to realize how the math magic has been performed and the illusion has been created in our minds, yeah, and how our lives have been standardized on this globe. That's what it's all about, standardizing our lives. and giving us rules and regulations and laws to follow. So really appreciate it. Thank you very much indeed, and we'll catch up soon. Thank you.